Today we're going to be talking about building secure cloud-scale disaggregated systems with capabilities, which has been an unsolved problem until now. So to illustrate security in the disaggregated cloud, let's take an example heterogeneous application consisting of a machine learning service running on disaggregated CPUs, an inference service on GPUs, and a storage service on SSDs. Now, minimizing the privileges that any of these services or devices have is essential. Take the example where a user wants to perform a classification on cat.jpg. Now, our disaggregated GPUs not only store cat.jpg, but also highly sensitive secret data belonging to other users and tenants. And if the inference service has access to any of this other data at this point, it poses a security risk. And if an attacker was to gain access to the inference service, this would open the door for them to exploit excessive permissions. So the way that existing cloud applications handle this is by writing an external security policy that all accesses are evaluated against. And this security policy tries to capture the minimal set of permissions required for all accesses in the system. And this is fine in a simple system such as this one, but in a more realistic cloud application, there can be up to thousands of microservices. And capturing the minimal permissions for all of these interactions and all of their complex application logic in a security policy becomes unfeasible, which leads to overprivilege in our cloud applications. So we believe that capabilities are a much better candidate for disaggregated cloud. To illustrate what these are, let's take an example where, the same example where the user wants to perform the classification, except now the ML service generates a token or capability that grants it read-write access to all of the user's data. This token can then be passed to other services or delegated, and the permissions associated with it restricted as it's delegated. And the inference service can then invoke this capability to retrieve the data from the SSD. Now, if the attacker is to gain access to the inference service in this case, they only gain read access to the single cat image and can't read any of the other data on the SSDs. And applications additionally can revoke access eagerly, which will then propagate the removal of permissions throughout the entire system. So this puts control of permissioning into the hands of application logic and essentially distributes the policy that was external before across all of the application code. So this can make privilege minimization scale much better to complex systems consisting of many services or interacting devices. But no capability systems are cloud ready, and this is because they need to perform in 3 key areas, and none can perform in all. So the first is scalability. We have very large data centers now, these are common, so a capability system must scale elegantly to this size of data center and be able to handle many new RPC connections per second. In addition, capability operations such as delegation and invocation must have very, very good performance so as to not discourage applications from using capabilities on the hot path. And we don't want to add too much overhead to our RPC solutions. And finally, fault tolerance. So failures are, of course, commonplace in the cloud, so we can't have these hindering the operation of the access control system. So existing works perform a trade-off between these 3 key factors, and commonly can perform well in 2 of 3 of the different factors, or perform very well in one of them, but poorly in the other dimensions. And yeah, so this is what all of the work falls onto this spectrum somewhere, but nothing can achieve all 3 of these factors at the same time. And this is our goal if we are to bring capabilities to the cloud scale. So to do so, we have 3 key ideas, and I'm going to explain the first to you now. So if we take a set of applications that want to access disaggregated devices over the network, existing capability systems centralize the metadata to do with capabilities. And this includes who owns which capabilities and which permissions they may have, among other things. And this means that all capability operation processing must be done in a centralized point. So, of course, the entire data center could be generating capability operation traffic. So this is going to result in a throughput bottleneck for the speed at which capability operations can be made. In addition, it creates a single point of failure. If that capability service is to fail, the entire system becomes unusable. So to solve this, we distribute the capability metadata into a network of controllers. And you can think of these controllers as being a lightweight service mesh that provides access to disaggregated resources and access control on those resources. So we move the metadata, for example, the capabilities granting access to GPUs into the controller next to the GPU service. And this kind of provides a natural sharding of all capability metadata among the available services. So it distributes all of the requests among these services, eliminating that throughput bottleneck. And it also isolates the failure domains of all the different services in the system. So the next problem that we seek to solve is the inefficient revocation of access in capability systems. And it's important that we can quickly revoke access to resources so we can give them to someone else who needs them for a higher utilization. So let's zoom in on the GPU service and its few connected applications. So what is that capability metadata internally? So it's a capability, what we call a capability table, which essentially is a key value store, where the key is a global capability identifier and the value is the capability itself, granting invoke rights on GPU3. Now, this is a distributed system, so other controllers can have access to this GPU, essentially by holding a key that points into the capability table. But what happens if the GPU service wants to revoke access to this capability globally in the data center? So we can't just delete that entry in the capability table because there are references to it globally. And we may eventually need to reuse that entry in the capability table because it's a finite sized data structure. And this would lead to use after free errors if we leave these references dangling throughout the system. So existing systems commonly broadcast the revocation to all participants. And only once every participant has responded can the entry be deallocated and the revocation terminate, deallocating the GPU. So this solves the problem, but also introduces O of N network messages, which is not going to scale well to a large data center, if we do this on every revocation. So to solve this, we associate a version number with every capability and capability reference in the system. And this version number gets checked every time someone wants to use a resource. It's checked that they have the correct version of the reference to the capability. This way, when we receive the revocation, we can immediately deallocate the entry, so long as we ensure that subsequent capabilities allocated to this slot have a higher version number. And this will implicitly invalidate all capabilities in the entire system. And that means we can very quickly deallocate the GPU and hand it to someone else. And we do this whilst requiring zero network transmission or CPU to process those network messages. So to evaluate this, we examine the impact on application latency of revocation for growing data center sizes and see that there are superlinear latency overheads with growing data center size for broadcast-based revocation. And with our version capabilities implementation, we only introduce a few microseconds on the tail latency, and this is a constant overhead. We perform a similar experiment examining the network transmission and model this to larger data center sizes and see that we have a quadratic increase in network transmission due to this broadcast when there's a fixed percentage of the nodes in the data center performing revocation. And our version capabilities implementation requires zero network transmission. So we also have all our capability operations such as delegation and revocation and invocation are on the low double-digit microsecond scale. So this is doing the RPC process as well as the access control. There's more evaluation on that in the paper. And to conclude, we have three key innovations. We didn't get a chance to speak about guards. There's more detail on that in the paper. So we use these to achieve all three cloud scale challenges, providing failure isolation, fast capability operations, and constant system overheads, regardless of the data center size. So thank you, everyone. And if you've got any questions.
Thank you. Very interesting work. Just one small question regarding the revocation of the capabilities themselves. So, do you see any, let's say, kind of implicit overheads that this may cause, in the sense that only when they're trying to realize these capabilities, they will fail later on? Whether, let's say, I don't know, you tell them beforehand and they choose, let's say, to fail much earlier and not go through certain paths that are required in the computational path.
Yeah, for sure. So it is, so we kind of propagate the information about the fact that a capability was revoked. We don't propagate that. We allow all the different participants in the system to lazily discover that their capability has been revoked. So there is going to be an RPC involved that didn't have to happen before on the client side. So that's going to have a higher latency. But I think it seems like a trade-off worth making because it eliminates, like, 1,000. This is an extreme example, but a petabyte per second of network transmission in a large data center. And this is just a model, of course, but it is based on real data.
Yeah, I'm a bit confused because like now you're basically pushing this, because as you said before, you didn't really require this RPC without this version flag, right? It's like before, when you invoke a GPU, you don't really have to do this RPC. Right?
What do you mean, sir?
Because you just said that now, after you introducing this version field in capability, every time a client invoking a capability, now they have to actually consult the source.
Well, wherever that resource is provided. So I mean, if you wanted to use the GPU, you have to follow this path anyway. Because you have to get to the resource.
Yeah, right? But where is the extra RPC then?
So it's basically whether or not this controller knows that it was revoked eagerly. So then application 2 can just contact its local controller and see that it was revoked immediately. That's in the broadcast.
It's the query that if the app decides to query the controller asking if this is revoked, now this requires another.
Exactly. Now you have to go all the way to this controller.
Yeah, okay. But if you actually just invoke it, then you will have to go to the.
You have to go to that controller anyway, so the overhead is not relevant.
This is really cool. So we have a capability table, and then you add versions, which are sort of an implicit table. What happens when you run out of versions?
Yeah, so knew someone would ask this. So you do eventually have to clear out or upgrade the old version numbers from throughout the system. But this is like a U64. So there are a lot of version numbers, and we have a lot of ways to slow this down. But actually, with very aggressive modeling, you see that this wraparound only happens in like once every million years or something like that. So then there are ways in which you can slow down the process of clearing out the old version numbers throughout the system to be essentially arbitrarily slow. You could clear one entry in one table every 2 years if you wanted to. So how efficiently you can spread that out determines the overhead on the rest of the operations. But that's not strictly measured here, and that's something that we should do moving forward.
Last one.
What happens when you need to, if you want to migrate a service, like as in the service provider? So you've got your reference monitor pins. You've got like a multi-kernel.
Yes.
You've got your reference monitor pinned to your service provider, and you want to, that fails out or whatever. You need to migrate, right?
So you need to migrate which part? Sorry.
Well, this service, the dog JPEG is now on this SSD.
Yeah.
Right, and this one's got a different controller, different reference monitor. All these other guys have, like, they all have references into here.
Yeah.
What happens?
So, if there's a failure in like a service that's providing an interface,
if for any reason you need to migrate the resource that's controlled by the capability to somewhere else, what does that imply for the?
Well, so this is not implemented, but perhaps you could do some. migration of entries in the capability table from one controller to another, such that, I assume that, I think that's how you would have to do
You're
it.
going to end up with some consistency protocol, and you might end up with a quadratic pair, right? Maybe, depending on how things work.
Maybe we can
Something to think
talk
about.
about
It's not a criticism, it's
Yeah,
just
yeah.
it's an honest
very
question.
interesting
I want
point.
to know.
Yeah, okay, thank you.
Great, thanks for all the questions and thank you.